Okay, let's look at Einstein's explanation of the photoelectric effect. What we're trying to do is get electrons to leave that surface. So electrons are negative, and this surface, if you think about it, consists of lots of positive nuclei in there within the surface. Okay, and you've also got electron shells here going on. And so what you've got to try and do is do work to pull that negative electron away from this lattice, this metal lattice of positive nuclei and electron shell arrangements. So there will be a minimum amount of energy needed to get this electron out, to pull it away from these positive nuclei. And I guess if you look at chemistry, electronegativity is going on here as well for different metal surfaces. So to do that sort of work, it's called the work function. And that's the minimum energy to get it out. So that's the minimum energy to remove it from the surface, and you can do that in joules or electron volts, okay? Now it's worth realising that there's of course a lot of other electrons in here that might be deeper or moving slower or in the wrong direction, and they'll require more energy than this. So these are the ones that are going to come off the fastest when we actually shine light on them. But there's going to be a range of them because some of them are deeper here or going slower or whatever, so they're going to be hard to get out. They require more energy. There's a whole range of those. So that's the first thing to realise. There's a work function to get this out. Now what Einstein did was take this idea that light comes in bundles of energy, okay, and they'd already knew that the bundles of energy had an equation. The energy of each of these bundles was E equals hf. So it depended on the frequency of the bundle. So if you had a fairly low frequency one, like a red light one, with a long wavelength but a small frequency, you had a small energy involved there, okay? So the photons were coming in bundles like this at about that much, okay? So they had a certain energy. If you had the blue light though, at the other end, blue light had a higher frequency and therefore had a higher energy. Okay, and so their bundles are worth more for each one, if you look at it. So that's something to bear in mind as well. Now what Einstein also said was that any one photon would only hit one electron in the actual process of photoelectric emission. So it was a one-to-one thing. Now that was a big difference between the wave theory here. The wave model said that as they came down, the wave's energy was shared to all these electrons, and so they should actually all come off together eventually, even if you use low light. So this is a key thing here. One photon will only hit one electron, and one electron can only be hit by one photon and being emitted. Because if it was hit by something else, it'll lose that energy fairly quickly, and therefore the photo emission would either occur or not occur. So it's a one-to-one thing. One electron is hit by one photon. So and the transfer is instantaneous, by the way. So this is an energy conservation thing. This energy coming in will all be transferred to the electron afterwards. Now, if this work function here is bigger, let's say it was 2 electron volts, than the energy of this photon coming down, right, the transfer would occur, but it would lose it pretty quickly. That would not be enough to get this to escape. It needs at least this much energy to escape. 2 electron volts. So you need to get these photons of energy here up high enough to get to escape. So you might have to go to a higher frequency and therefore high energy, and if this is bigger than that one, the energy of the photon is bigger than the work function, you will get emission. That's what he's saying there. On top of that, if this does have a high enough energy, let's say it's got an energy of say 6 electron volts, and we needed 2 electron volts to escape as the work function, when it's transferred to this electron here in the collision, what's going to happen here is the electron is going to take that 6 electron volts, it's going to use 2 to get out, okay, and the rest of it is going to become its kinetic energy as it leaves. And in this case, for this electron type, which has got the minimum energy to get out, it's going to give you the maximum kinetic energy possible. All right. So if you look at that, the energy before of the photon equals the energy of the electron, which is this idea of hf is equal to the work to overcome there plus the kinetic energy left over. If you look at the numbers, it'll be 6 electron volts is equaling 2 to overcome that work function, plus another 4 left over for kinetic energy maximum. All right. Now you can rearrange this formula here for kinetic energy maximum. You'll see it on the formula sheet. Kmax equals hf minus w. So let's have a look at this. If you're trying to work out the kinetic energy maximum of the electrons leaving here, okay, it's based on the photon's energy coming in, which is 6 electron volts coming down. Subtract the work to get it out, 2. So you're left over with your 4 electron volts of kinetic energy maximum. And that's the most you can get. Now, of course, some of these are actually require more work than this because they're deeper or slower or whatever. So therefore, you're going to have to use more work to get it out. So more energy is needed. So they might not come up with as much as 4. So some of them might require 3 to get out, for example. In which case, 6 take away 3, you only get 3 electron volts. So this is the maximum you can get. There'll be a range all the way down to 0 here. You find a range of energies explained by this model, and that matched what happened in the experiment. So let's just look at some key points here and add a few more. So the light comes in bundles of energy, discrete bundles of energy given by E equals HF, so it's proportional to frequency. And we can call these an individual one a photon or a quantum of energy. The plural to that is photons or quanta, by the way. When one photon hits one electron, it transfers all of its energy instantaneously. And don't forget, an electron can only be hit by one photon, so it's a one-to-one transfer of energy. We don't consider any other sort of situations. Now, there's a minimum energy needed to get the electrons out, and that's known as the work function. And what we're saying here is if the energy for the photons is bigger than the work function, they will get a release. Okay? If it's less than the work function, they will not be released. And we've actually got a formula here to work out the kinetic energy of the electrons as they come out, and it's HF minus W. But that, don't forget, is based on the fact that the photon's energy is being transferred to the electron, so it's doing work on the electron and the rest of it's going to K max. Okay? So it's that sort of transfer. So it is an energy conservation before to after. Now the last thing I hadn't pointed out here was this idea that if you had more intense light, then what Einstein said was more intense light would actually mean more photons coming down. So each photon bundle will be the same, but if you increase the intensity, you'll end up with more photons. Now that means you're going to get more interactions with electrons, more collisions going on, so more electrons should be released. So let's see how that matches up with the experiment that they did. So this experimental arrangement, what we've got here is we've got light shining onto the metal plate there, and we're going to actually get this collecting over on the other side. So what we're going to do here is we're going to turn up some intensity here, and we're just going to use red light to start with. Now you can actually show the photons as well. So we're showing the light here as photons. So obviously more intense light will be more photons. Okay, less intense light, less photons. All right, so less collisions here. So what you would do is give this a certain intensity. You'll find at the moment there's a threshold frequency here that we've not gone above. So the red light has not got a high enough frequency for any one collision to release any one electron. But if we raise this up a bit and try and get to a minimum frequency here, we're getting into green maybe. We get some electrons just starting to come off, just about there. Okay, so this must be really close to just being above the threshold frequency. Okay, so you get to see electrons going across here like that. So we can measure how much current. Now, at the moment there's virtually no current there because this is probably just too close there to the bottom. So let's just go slightly bigger. Okay, now we should start to register a current here with a bit of luck. Okay, so I'm using a microamp here, and we've got this actually big enough to measure current coming through of 0.034 amps, or probably 0.034 milliamps in actual fact. And we're not using any voltage moment. So we can see that if you increase the intensity of the light, we will change the current here to 0.049. Okay? If we decrease the intensity of the light and have less photons colliding there and less electrons coming off, the current will drop off. In fact, I've dropped it right down too much here. Let's just pick that up again. All right, so intensity does have an effect on the current. So that was one of the things they discovered. Now that's explained by Einstein's model because more photons means more collisions, more electrons coming across, more current. Okay, that's the first thing. And this transfer was instantaneous, by the way. If you turn the light on, you instantaneously get a transfer of energy and the current appears instantaneously. There's no measurable time delay with that. All right. So apart from measuring the number of electrons coming off here, you can also examine their energy. So what you can do is turn these around by actually setting this up as a negative plate and a positive plate. And so you've got an electric field here that the electrons are now working against. Okay? So they will be turned around if you turn this voltage up big enough. So let's just turn this up to minus point. Now I just put minus 0.1 volts there. So what I've set up here is a situation where that's enough to actually turn some of these electrons around that are going a bit slower. But the faster ones are still making it across, if you see that. So in the experiment, what they would do is they would keep turning this voltage up, this reverse voltage or stopping voltage up, until this current drops down to 0. Okay? Minus 0.3, the current's gone down a bit more and we're turning some more around. You can see some of them get sort of turned around when they get about halfway at the moment. You turn this voltage up, this stopping voltage, until the current has just dropped to 0. And what you should be able to see happening is some of them are turned around fairly quickly here, a shorter space because they've got less energy, but some of them are making it all the way to almost touching this plate here, almost touching the plate. Now, based on that then, we've just stopped the fastest ones, the ones with the most kinetic energy, the Kmax ones. So the energy they must have had to start with to overcome this electric field, because their kinetic energy is being turned into electrical potential, delta VQ, they must have had 0.53 electron volts to start with of kinetic energy, and that's about what they've as potential energy just here, not quite enough to get to that plate. Okay, so we can now get an energy value here based on this stopping voltage of 0.53 electron volts that matches the kinetic energy of the electrons. So we know for this particular frequency of light what the highest kinetic energy electrons were. Now, other experiments they did here is they found out that if you change the intensity here, is that does not affect the stopping voltage here. It does not give you any more energy to any of these electrons, because they only get their energy from one photon according to Einstein, and that's consistent with what he said. Now, if you try higher frequencies, it turns out you'll get higher stopping voltages. So it's possible to draw a graph here where you actually change the frequency by changing the filter going for that each time, or changing the colour of the light source, and you'll get a point there of the Kmax for each one based on the stopping voltage. So you could do this in electron volts, getting it directly from the voltage or the potential difference there. So let's say for a certain frequency we've got a value here. Okay. When you try other ones by changing the filter here, you'll get something that goes like this. Okay. So a line of best fit might look something like this. Okay. As you increase the frequency, we do see the kinetic energy going up, which is one of the observations. All right. And the reason for that is, of course, the photons have got more energy because of the higher frequency, and therefore the electrons are released with a greater kinetic energy maximum. So that's explained by those results. At some point here then, we said there was a threshold frequency, a minimum frequency needed, and that's also predicted by Einstein there, because there's a minimum work to get the objects out, to get the actual electron to leave. You need a photon of at least that much energy equal to the work function for this to happen. So obviously, there should be a minimum frequency energy here of this photon. The photon needs a minimum energy to match the energy needed to get this out. Now you get quite a nice formula for this. This is a y equals mx plus c graph. Now if you look at it, the y is your Kmax. Your slope there would actually turn out to be Planck's constant, believe it or not, as the slope. That's where you get Planck's constant from. The x quantity is f, and your intercept here, your y-intercept, is actually going to be the minus w here. It's minus the work function. So if you've got a value of 2 electron volts, or minus 2 electron volts, because in the negative here, okay, that means your work function was 2. Okay, so that there is one of your few linearly dependent pairs of relationships between Kmax and frequency. This is not directly proportional. You've got an intercept here, so this is linearly dependent. Okay, thanks.